My heartiest warm welcome to our guest speaker, who is a great mathematician and our alumnus, Dr. Pramod Kanwar, and our principal, who is well acclaimed, and of course, a very magnanimous person, Dr. Rajiv Agarwal, all faculty members from all the different colleges of Delhi University and across India, and of course, my dear students. Now, my sincere gratitude to our principal, Dr. Rajiv Agarwal, for his continuous support and motivation and inspiration for holding this type of series, Kshitij Mathematics Lecture Series, under which this program is being hosted. He is always inspiring force to go through these academic activities time to time. And I must mention here that for the last 2 months, this is our third series lecture in this series, and he always inspire us to take the plunge into these type of activities and do whatever you can do for the benefit of the student. And this webinar is a perfect platform for the Kshitij Mathematics Lecture Society, who believes in the development of the complete persona of the students, which can help them to stand out in this academic competitive atmosphere. So our sincere gratitude to my team, organizing team, and of course, appreciating their efforts. I congratulate our teacher in charge, Dr. Chandrasekhar, and all my team members for executing and planning this event so well. Now, they have really put up their heart and soul to organize this event, and it is all due to their efforts, continuous efforts, that we are here today for this webinar. Now, as an undying tradition, we have to always start any academic event with the Saraswati Vandana to seek the blessing of Ma Saraswati, who is goddess of learning, intellect, and wisdom. Please join us in this prayer for the Saraswati Vandana. So let's start it.
श्वेत वर्णी कमल पे विराजे, हाथों में वीणा मुकुट शिर पे साजे, मन से हमारे मिटा दे अंधेरा, हमको उजाला का परिवार, आशा गम की वाणी, संतों की भाषा गम की वाणी, हम भी तो समझे जाने, विद्या हे शारदे माँ, हे शारदे अज्ञानता से हमें तार दे। तू श्वेत वर्णी कमल पे विराजे, हाथों में वीणा मुकुट शिर पे साजे, तू श्वेत वर्णी कमल पे विराजे, हाथों में वीणा मुकुट शिर पे साजे, मन से हमारे मिटा दे अंधेरा, हमको उजाला का परिवार दे माँ, हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे।
Sorry, there was some technical glitch. So may Goddess Saraswati bless us all and make us free from the shackles of this pandemic, COVID-19. Hope normalcy gets back very soon to our campuses. World is full of diamonds and gems. We are having some of them here today to celebrate and build this event. A revered mathematician, distinguished young educator, a great researcher, an excellent administrator who is none other than our principal, our dear Dr. Rajiv Agarwal. I request him, Dr. Rajiv Agarwal, for his formal welcome address. Dr. Rajiv Agarwal.
Thank you, Usha ji, for the nice and worthy introduction. A very good morning. On behalf of Deshbandhu College fraternity, I welcome all the mathematicians, all the participants, researchers, students from University of Delhi, from other universities of the India and abroad. Today, I again welcome you to the lecture series, mathematics lecture series, which is being organized by Mathematics Society Kshitij. The title of the talk is Journey from Integers to Rings. Seems to be very interesting. My special welcome and thanks for today's speaker, Professor Pramod Kanwar. I am fortunate to have been taught by Professor Pramod Kanwar. He is very passionate teacher, passionate researcher. Perhaps I was the last batch or second last batch who was taught by him in Crodimal College. Friends, I share you a very interesting incident. Like he taught us dynamics, which is not being taught in colleges at undergraduate level in University of Delhi. Of course, the first day, all the students were introduced to Professor Pramod Kanwar. Somehow it happened the next day, very next day, I could not attend his class. But very surprisingly, in the next class, he called me and said, Rajiv, where were you yesterday? I was surprised that he remembered my name in the next class, and the class was consisting of almost 45 students. From there, I could find that he may be remembering the names of all the students. And then, of course, it was a history that he taught us dynamics, and because of he was one of the person by which I was inspired, and my research field was also related to dynamics. He taught us a subject which was not his specialty. He was expert in algebra. Later on, he did his PhD in algebra under Professor S.K. Jain. He went to US over there, and ultimately he resigned from Crodimal College. So, sir, many thanks that you have accepted our offer. You are a proud alumni, and we are also proud of you that you are an alumni of Deshbandhu College as well. So, in a way, I have got two connections from Deshbandhu College and from Crodimal College as well. In the end, my heartiest congratulations to Department of Mathematics, Deshbandhu College, Dr. Chandrasekhar Azad, Dr. Harindri, Dr. Usha Arora, our IQAC coordinator, for organizing this wonderful talk. Thank you very much. My best wishes to all of you.
Thank you, sir, for your inspiring words. Now is the time for the introduction of the speaker. Algebra is the weapon of maths instruction and is known as Picasso of mathematics. Today, we are honored and fortunate enough to have among us a great mathematician with specialization in algebra, Professor Pramod Kanwar, who is going to speak on the topic, a journey from integers to rings, a very fascinating one. We thank you, sir, for accepting our invitation to join us and sharing a part of your oceanic knowledge to our students as well as to the teachers, and especially from the algebra. It's my pleasure to give a brief introduction of Dr. Pramod Kanwar. Born and brought up in Delhi, Dr. Pramod Kanwar is now a professor of mathematics at Ohio University, Janesville, USA. Before moving to for the higher education to USA, he was a senior lecturer at Kirorimal College, Delhi University. In fact, he started his teaching career from Delhi University, as our principal sir told that he was a student. I'm glad to know that we have so many relations with Dr. Pramod Kanwar. If I'm not wrong, sir, are you brother of our botany teacher, Dr. Anju Chibbar? Someone told me. Is it right?
That is correct.
Oh, thank you, sir. Thank you so much. So it's my pleasure again that I have to introduce such a person who is related to us in so many ways. An alumnus of Deshbandhu College, Dr. Kanwar started his teaching career as a lecturer from University of Delhi, as I told you, from KM College. He is widely traveled and has also held visiting positions at Rouen State University and Artois University, France. His research interests include theory of rings and modules and algebraic coding theory. He is author or co-author of several research articles published in journals of international repute. He has presented his research papers at various national and international conferences, also organized national and international conferences. He has also edited research volumes published by American Mathematical Society in its Contemporary Mathematics series. He is the organizer of Math Morning in the life of high school students, an annual event held at Ohio University, Janesville, in support of Mathematics and Statistics Awareness Month. Deshbandhu College is proud of you, sir. We are very happy to have you here. How can I forget to mention his accolades? He has got so many accolades, as Principal Sir told that he's a very good teacher. So it shows that how many awards he has got due to his best teaching. Recipient of Lapsing Gold Medal Award from Deshbandhu College for securing first rank in BSc Honors Mathematics. He is the first mathematics faculty at Ohio University who has given the status of presidential teacher for excellence in teaching and meritorious academic pursuits, both inside and outside the classroom. Recipient of Dean's Outstanding Teacher Assistant Award for excellence in teaching here, and the Regional Higher Education Outstanding Professor. Ohio Magazine has also given him the recognition for his contribution and dedication to achieving excellence in education. So we can see all these awards show that he has been very good teacher, and he has, of course, he's earned his name and fame in Ohio University also as a good teacher. Without wasting time, now I request him to start his presentation. And before, just one announcement, that please post your queries during his presentation at the chat window. Our moderator for today, Dr. Pankaj Mishra and Dr. Preeti Gupta, will take the queries after the presentation. So over to you, sir, for your presentation.
First of all, I'd like to thank the Department of Mathematics, Dr. Hendri Chaudhary, Dr. Usha Arora, Dr. Ajad, and the principal, Dr. Agarwal, who now you know that he was my student, and he is correct that it was the last batch, or the second last batch that I taught at Kirodimal College. First of all, I would like to thank everyone for giving me this opportunity to talk to you people who are at an institution where I got my foundation from. It's the Deshbandhu College that gave me my foundation. That's when it started. My college, I lived very near Deshbandhu College. So obvious choice was Deshbandhu College. I didn't try any other place. I just went there. And then got the foundation, got a job in Delhi University, and then left the country. I was surprised that Dr. Agarwal remembered that I called him the second day. So Rajiv, that's my habit even today. At Ohio University, although nobody does that, I still call upon students when they are missing the class. So that did not change even after coming to Ohio University. I'm proud to be with you people because I'm alumni of Deshbandhu College, and it's always a good thing to be back from where you got your education. And so it's because of Deshbandhu College I'm here. It's not, no other place. That's the one that gave me foundation. Dr. Arora, although she didn't teach me, she arrived around the time when I was there. But all of the teachers, my teachers are now gone. They retired. So I think the last time I was in Deshbandhu College, I gave a presentation. Some of my teachers were still there. But I can assure all the undergraduate students who are attending this lecture, you are at the right place. The faculty at Deshbandhu College, your principal are caring. If my faculty was not that caring, I wouldn't have been here today talking to you people. So when I was approached by Dr. Chaudhary, I immediately agreed that, okay, I will get a chance to talk to people. I would loved in case I was able to talk to you people in person, but because of pandemic, I'm not able to. So maybe sometime in future when I'm in Delhi, I will be able to, I'll just stop by and chat with you people. I'll give that, I'd like to have that opportunity when I can just sit with you, just chat. So I will probably get a chance sometime soon. So we'll do that. But under the circumstances, we will connect this way. And I approached Dr. Agarwal also about this talk, and he said it's undergraduate students. And I see here several faculty members are also there. from different colleges, and where basically I decided about this topic because when I joined as a math major, math honors student, it was my high school teacher who kind of pushed me into this. He decided my career, he decided my education path. But after joining, when I went to him, he immediately kind of discouraged me. He said that he gave me an example that was a negative example. So I told him, you already told me this is what I should do, and I'm not changing my mind. When you join this math honors, you have different ideas. I do not know how many of you, and maybe since Dr. Agarwal is here and he's my student, I can always call upon him and ask him his impression after he joined math honors at KM College in the first year, whether he expected exactly what he saw or he was disappointed in the beginning, although later on he got PhD. Because in the live classroom, I can ask this question, but right now, so Dr. Agarwal, a quick question for you. That is, when you joined in the first year after high school, having high school experience of mathematics, is that what you thought math honors would be, or you thought something different?
Sir, at my time, at our times, the syllabi were different. So first year was, we can say, extension of high school, but second year and third year was entirely different.
That is correct. And then you were disappointed at that time?
No, not at all. Not at all.
So you got some time in the first year to catch up, and therefore. But these days I see at the very first year, you start doing all the proofs, etc. And the students, I was giving a talk in another institution, and it was live. I asked the questions and almost everybody in the classroom said, no, we did not think that is math honors. This is not mathematics. So keeping that in mind, I prepared this lecture. So let's start, and I will share my screen here with you, Pearl. I hope everybody can see my screen.
Yes, sir.
Yes, sir. Yes, sir.
Okay, so I'll start with how my journey or anybody's journey of it starts. I'll start from elementary school and take you to some research problems that very simple ones, which of course you can try those things and get the answers. So how the things transition. So here is when you're in elementary school, you talked about numbers. Initially, you did not use the word integers. Rational numbers, fractions, everything was in elementary schools. Real numbers. Of course, how to add all that stuff. Nobody used the word ring. Multiplication, etc. That was what was in. When you transitioned from elementary school to middle school, you started talking about properties of all these addition, multiplication, etc. Introduction to X, Y, Z, A few years ago, I was giving a presentation. There was somebody else from Indira Gandhi Priyadarshini University, and she was giving some introduction to these kids who were first year, second year, third year students. And then her statement was, when you got to the middle school, chhati mein chhati ka doodh yaad aa gaya. So that's the phrase that was used. So you got polynomial expressions and how to add, multiply those polynomials. All that was in middle school. And you had properties of addition, multiplication, etc. And what are those properties? You are familiar with those now. Commutativity, associativity, property of zero. I'm not going to those. Everybody knows these. Existence of negatives, multiplication, also commutativity, associativity, multiplication of 1, and the distributive property. Integers did not have reciprocals as such. One of the things that you saw until then, the product of two numbers is 0, then one of the numbers must be 0. If the product of two numbers is 0, then at least one of them must be 0. That's for polynomials also, for numbers also, everywhere you had that. When you get to high school, you got to complex numbers. You learned how to add, multiply complex numbers. These properties were same, addition, multiplication, everything was still same. And you introduced the matrices also. Of course, you took matrices over real numbers. You saw how to add matrices, multiply matrices, how to multiply matrix by scalar. All these things were in high school. And these same properties, almost same properties, were there for addition and multiplication of matrices. One thing, there was a noticeable change here. You could not add any two given matrices. There were some restrictions. Some conditions were applied. For example, to add matrices, they had to have the same size. To multiply, the number of columns of the matrix A must be same as the number of rows of the matrix B in order to define A times B. So all those restrictions were there. And that did not happen before anything else, in any other things. Then you saw that multiplication was not commutative. Now, sometimes the multiplication was not even defined in one. For example, A times B is defined, but B times A is not defined. So that was first thing that you saw where there was no commutativity for multiplication. Another interesting thing that you saw, that you multiply matrices, non-zero matrices, and you could get 0. This was not the case before. For anything, I mentioned that as a crucial and critical property there. I gave it an example. You can make several different examples. You're familiar with that. Everybody in this room must be familiar with that, even if you're a first-year student. Everybody has seen this. It's also possible to have a square matrix whose square is 0. or cube is 0, or some power of that is 0. These things do not happen in numbers. For example, if you take a to be 0, 1, 0, 0, then a square is 0. Why I'm bringing these up? Because these are my interesting elements. And I will be talking about that. Here's our matrix. And this one, a cube is 0. The matrix is 0, 0, 1, 0, 0, 0, 0, 1, 0. You can check that a cube here is 0. Another interesting thing is that you can have a non-zero matrix which is not equal to the identity matrix, and still a square is equal to a. There are several examples like that in matrices. For example, both these matrices that are written here, we can see that their square is same as the original matrix. Now you'll say that I'm making the matrices in such a way that has to happen, that will happen always. And because I'm taking either 0 row or 0 column and picking my numbers carefully. The question can be, can we have a matrix with all entries non-zero and still a square is same as a? So can we have a matrix which is non-zero matrix, of course, with all entries non-zero, such that a square equal to a? Any guesses? I see some chat answers. Answers are coming. Yes. I don't want the identity matrix. Somebody wrote identity matrix here. Identity matrix will not have all entries 0 or non-zero. I want all entries to be non-zero. All entries has 1, that will not do the job either. Okay, answer what you were telling me. Yeah, these are the idempotent matrices. I didn't bring the name yet. Okay, I have an answer, not possible. Okay, good. I'm glad that people are participating here. I'm not interested in 1 by 1 matrix. I know 1 by 1. See, 1 by 1 matrix is just a number. Okay. So, not possible. Okay. Okay. So I'll answer the question now. Okay. I'm glad people participated. All non-zero, not possible. Okay. But see, it's correct. Idempotent matrices. Now I hear somebody saying possible. Yes. So give me an example. So let me tell you, the answer is yes, it is possible. Yes, it's possible. And I'm still talking about real numbers only. I'm not changing anything yet. So in real numbers only, it is possible. I'm finding, okay, No, that will not do the job. Okay. Okay. Okay, I have another answer from somebody, and that is not correct either. That will not do the job. I like it that people are participating. So we can do these things remotely when people can participate also. That's great. That's good one. Somebody gave an answer, and that will definitely work. Okay, and the next one that I'm coming is not going to work. Okay, so let's stop here, and I will do one thing. I'll tell you something in a minute, and what I'm going to do is stop this share. I'll come back to this and share a different screen. So here is what we're trying to do. Everybody can see my different screen here, I believe. So the answer that somebody gave me is this one: 1/2, 1/2, 1/2, and 1/2. And that's correct. Let me give you another one. Three eighths, 5/8, 5/4, 3/16, and 5/8. That will also do the job. You can check that. If you take this matrix to be A, then A square will be same as A. Now you'll say, how do I know that? Both these matrices that are on the screen right now satisfy certain properties. If you add the diagonal entries, A11 plus A22, that's equal to 1. Both of them have that property. And the second property that both of them have is the product of the diagonal entries is same as the product of off-diagonal entries. Both these have that property. So anytime these two conditions are satisfied, and note that I'm talking about only the matrices at this point with real numbers, although this is true other places also. But since some of you do not have the full knowledge of ring yet, so I have not gotten there yet, this is always true if these two conditions satisfied. Anybody who's interested in, you can try to prove this, that if you have a 2x2 matrix A, B, C, D, just take real numbers. If this is the thing, and then A square is A, then you must have these conditions that A plus D is 1 and A, D minus BC must be 0. And this, even if you just got into first year or you're a second year student, everybody should be able to get these conditions. So that's an interesting way of looking at these elements. Now you might say, why I'm so much interested in this? I'll tell you this. These are very important elements. These, now somebody used the word idempotent. Yes, these are called idempotents. And there are nice properties of idempotent, and they play a critical role in ring theory. So I'm going to unshare this, and once again back to my oops. So answer to this question, of course, we now know the answer. Answer is yes. And here also I wrote an example, which is not same as the ones that I gave you there. I just wrote something else. So once again, you see that same property is satisfied, that diagonal entries, when you add them, you get 1. And you multiply diagonal entries and multiply the off diagonal entries, their products are same. So these are the conditions for a 2 by 2 matrix. This is for 2 by 2 matrix only. These conditions must be satisfied. Okay, so let's continue. So what remained the same? Commutativity, associativity, everything stays the same for addition. Multiplication lost commutativity. And of course, if I'm taking square matrices, you did have the identity matrix, which I didn't put down here. Let's continue. So once we went to college, we just entered a completely new world in the very first year. What changed? Abstraction. Things became abstract. Axiomatic approach. And the problems kind of started to look more like this. So what is this problem? What I'm saying is, suppose that X is a 3-digit number, with the condition that the digit at the units place and hundreds place, then first and the last digit are not the same. Y is the number that we obtained from X by reversing the digits. Let's take Z to be, now if I say Z, do you know what I mean? Because I have a habit of calling Z as Z here now. So I'll keep in mind I don't do that. So Z is equal to absolute value of X minus 5, and W is the number obtained from Z by reversing the digits of Z. Thinking of that as a 3-digit number. For example, if the number is 57, we'll consider 057 and make it 750, although you'll not get 57. So prove that Z plus W is a constant. So the problem is like this. So what is happening here? Or the problem would look like this. It's the same problem. In the first case, I said prove that Z plus W is a constant, where the second case I'm saying find the value of Z plus W is the same problem. Anyone has any idea what I'm talking about here? Let me tell you, this is not a problem that I took from a book or anything. What is it? It was a game I used to play as a little kid. As a child, we used to play a game, and I converted that game into this mathematical problem. So if you're a first year student, second year student, you see this problem. So it happens, what's going on? How do I even start with this problem? So let me see. Okay. So if you're first year, second year student, immediate reaction is I'm completely lost. I'm completely lost on this. So what do you do when you are given a problem like this? Your math teacher, in an abstract problem like this, they gave you a problem and then you're completely lost. So what do you do? The first solution of such a problem is very simple one. But that's not the best solution. And that will not take you anywhere. So what is the first solution? As easy one, give up. And we can be tempted to give up as soon as we see a problem like this and say, okay, I don't know what to do. I just give up and then leave right there. But that's not a good solution. Should never give up on any problem. So do what? Try it. Now say, how do I try? There are several ways to do that. One thing is you have some ideas, start proving. If you don't have an idea, take some examples. So either you can try completely or try with the examples, see what's happening, because I'm trying to find the value of z plus w. You can just take numbers, see what happens. You try 2-3 examples, get different answers, and you can get some idea. Now, I already told you in the problem, it's a constant. So if you try 2-3, and then that will give you an idea what would happen. Yes, I see the answers. Okay, somebody saying I've done without examples. Good. So that's just in case you can do it directly, that's great. But otherwise, try with the examples. And I see the answer also. Somebody gave the answer. And what's going to happen here? So after we try with the examples, now you conjecture and see what you think. The value will be 1089. And I want you to prove it as this is homework. And you can give your solution, especially I'm talking to the first year, second year students, not the teachers. So try it and you can give your example to your teachers and they can check that. Or they can have them sent to me. And so that I know how many of you tried it. So that's, you can try it. What you do is write the based on representation of the number and it's simple algebra that will get you there. So write the number as a times 10 square plus b times 10 plus c and things like that with the digits a, b, c. You remember that you have to use the fact that a and c are not the same. And this number 1089 is an interesting number. It's a pretty interesting number. If you multiply this by 9, you end up getting the number which the digits are reversed. And this is the only 4-digit number that does that. There are several properties of this number 1089. So what is a ring then? All that I was talking about all the time, that was a ring. All those commutativity, everything, that's exactly was my ring. So that's what when I was in college, when I learned the ring, that's where I saw that everything I knew, but nobody told me that was a ring. So the properties are same that we're talking about. And of course, since multiplication is not commutative, so you have to have 2 different directions of distributive property. So that's where our rings are. There are 2 different types of rings, commutative and non-commutative. See, commutative is algebraic number theory, which you have Fermat's last theorem. Finding integers, there are sums of squares of two integers. That's a problem also. In commutative, you have algebraic geometry. And the study of algebraic curves. And the Dadigan rings and ideals. So Dadigan used the term domain of integers. He didn't use the word ring. He used the term orders for the set of algebraic integers that are closed under addition, subtraction, and multiplication. Hilbert coined the word ring. Some historical things here. That's what I'm talking about, historical journey of this. His work relates to the problems in algebraic number theory, and that helps solve these problems in algebraic number theory in special cases. So this is a complete thing. Under the algebraic geometry, you have algebraic function fields and polynomial rings and ideals in polynomial rings. And non-commutative, first example was of quaternions. And that was in 1843. This was introduced by Hamilton. As I mentioned, that is the first example of a non-commutative number system. And this helped exploring number system with properties different from those in the case of real numbers and complex numbers. So this was a non-commutative example, the first one. So their properties were different here. This is Fermat's last theorem. The equation x power n plus y power n equal to z to power n has no integral solution for n greater than or equal to 3. This remained unsolved for several years, over 350 years. It was solved in 1993, the first solution, but that was incorrect. This was later solved a year later after that problem was fixed. So Andrew Wiles gave the proof of that problem. So this first proof came in 1993, but that had a problem and it took more than a year to fix that. So, but this problem is solved, don't try it. So this is where integers were not enough and they had to go outside the domain of integers to solve this problem. So that's what it's a long proof. It's not just a one-line proof. So it's a nice proof, and anybody interested should look at that to get new techniques. So coming back to my rings, some of the elements that are of interest. This is one thing that somebody used the term idempotent. These are those elements that satisfy the property A square equal to A. These are interesting elements. They give us the decomposition of rings and modules. And that decomposition helps us study those things quite a bit. Nilpotent elements, that is also I introduced earlier, that elements that satisfy the condition that 8 power n is 0 for some positive integer n. These are all interesting elements. Units, that is invertible elements. And these are different problems like getting all the units of ring, especially in the group rings case, getting all these units is an interesting problem. And lots of efforts have been made to get the solutions of, or getting the units. Getting the unit group of a ring is an interesting problem. Clean elements, that of course, as undergraduate, you may not have heard that. These are those elements that can be written as a sum of an idempotent and a unit. And this plays a critical role in C-star algebra. In fact, the ideas came from there only. I already mentioned that the set of units is an interesting thing. It forms a group, and it's called unit group of the ring. If you take the ring of integers modulo 6, see idempotent. Now, those of you who have not seen integers modulo 6 is essentially you add and multiply by simply regular multiplication, but take the remainder after you divide that by 6. So idempotents are 0, 1, 3, and 4. Nilpotent elements, it has none. Units of 1 and 5. And every element in this is a clean element. Now, the elements, a ring in which every element is clean is referred to as a clean ring. The ring of Gaussian integers, these are complex numbers, but those of you are not familiar with, these are same as complex number kind of, but you take integers in place of real numbers. So here, idempotents are only 0 and 1. So 0 and 1 are always idempotent in any ring, and these are called trivial idempotents. And we are not that much interested in them. We are interested in the ones that are non-trivial. And that's what we keep looking, where we have non-trivial idempotents, because those are the ones that give us all the decompositions. Nilpotent, no non-zero nilpotent elements either in this case. There are 4 units in this case. These are only ones, and we can always check. We can find them. 1, -1, I, -I. And clean elements are, these are the only clean elements in this ring. So here, not everything is clean. So this is not a clean ring. Even the ring of integers is not a clean ring. Some ring extensions, the matrix rings. Now, normally we were doing early matrix over real numbers, but we can make matrices over any ring, commutative, non-commutative, anything. Addition multiplication is exactly the way we did with real numbers, but you have to be careful. If R is not commutative, multiplication, you have to be very careful how to do those things. Multiply. If R has 1, then the matrix ring also has 1. So if R is any commutative ring, and this is I wrote that as a question, but you can easily prove it. And this is one of my results. We needed that, so we got that. So R is any commutative ring, not just real numbers. And ring has no non-trivial idempotence. Then the trace of every non-trivial idempotent in the 2 by 2 matrices is just 1. So that's one thing. It's not difficult for us to prove, but we needed that. So, and this is only for 2 by 2 matrices, not for, if you go higher, then it will not be the case. Another thing is R is a commutative ring with no non-zero nilpotent elements. Then the trace of every non-trivial idempotent lies in the base ring. So the trace will be coming from the base ring. Now we're talking about matrices, and we can connect the matrices with graphs also. So here I'm taking a graph with 2 vertices and 1 edge. They're connected with 1 edge. We take another edge here. What is the ghost edge? It's the edge that, see, E is the edge from V1 to V2. So E star is edge, same edge, but in the opposite direction, V2 to V1. We introduce some constants, that V1 square is V1, V2 square is V2, V1 V2 is 0, and V2 V1 is 0. That's not it. There are some others. The edge E1 is same as E1 times the vertex V2, or the V1 times the vertex E1. And similarly, E1 star is even, the ghost edge is E1 star V1, which is same thing as V2 E1 star. And E1 star is V1, and E1 star E1 is V2. If we apply these restrictions and generate the algebra, we get 2 by 2 matrix ring. Now, I'm giving this a very specific case of a big concept, which is the hot topic these days in ring theory or algebra. A lot of people are working on that. It's called Leavitt path algebras. So mainly the work is done over fields, but several people have started to work on Leavitt path algebras over rings. So I gave you only this one example where we get the matrix rings. But you can get different algebras using different types of graphs. It's not just for 2 by 2 matrices. Even if it's 3 by 3, that also can be obtained by a different graph. You can take this graph with 3 vertices and 2 edges, or you can take this graph, 2 vertices with 2 edges. Again, you'll have to take ghost edges and similar conditions. There were several of them. Of course, we can combine them into single relations, but we add those conditions and generate the algebra. We will get what is called the 3 by 3 matrix ring. In fact, the top graph here with 3 edges and 3 vertices and 2 edges, this is referred to a line graph. And in case we can take n vertices and n minus 1 edges like that only, that will give us an n by n matrix. So what I'm saying here is, in general, we can do the following. So if I take V1, V2, V3, and keep going, Vn, and then take edges E1, E2, En minus 1. So n vertices, n minus 1 edges, and similar conditions. There are several conditions there. Actually, there are 4 conditions, but we had to write that for every vertices. Then it's called, this will give us MNR. Instead, I can even do just 2 vertices, and I take all these edges right in between.
Sir, sorry to interrupt, sir. Your screen is not visible. Sorry,
Oh.
sir. Your screen is not visible.
The screen is not visible? I don't know why. Let me see.
We can't see.
Okay. Let me show that. Do that again. Can you see now?
Visible
Yes,
now.
yes, sir.
Yes, sir.
Okay. 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 So I will do this thing then so that I can redo what I was doing. Sorry about that. So what I was saying is, what you do is n vertices and n-1 edges. All the vertices are in the same direction. All the edges are in the same direction. You're not coming back. Then you would get n by n matrices. The benefit of that sometimes is, of course, not for matrices because we are so much used to matrices, but in general, using these kind of graph algebras, these help us study and make our life easier. And you can, instead of doing this, I can even do this part. I just take two vertices and then take all these edges in between them. If I take 3 of them, I will get M4R. All of them have to be in the same direction. I cannot have a loop here. So I cannot come back. If I am able to come back, then of course it will not give us, because it will form a loom, it will give us a different algebra. So that's a connection between matrices and the graphs, and this kind of things, the graph algebras, what I'm calling them Leavitt path algebras. Because see, some of the faculty is also there, so they might be interested in. So you can find the Leavitt path algebras, and this is one of the topics that's pretty recent. In the last 10 to 12 years, a lot of work has been done on this one, and a lot of people are working on this at this point. And mostly the work was done over a field, but some people also have taken arbitrary commutative rings. You need commutativity. So I'm stopping this one. I'll come back to my presentation back. So just checking, everybody can see my screen again, the new one.
Yes, sir, we can see.
Okay, good, thank you. So that was one thing that I wanted to share. So some other extensions, the polynomial rings are also interesting rings, and you can do lots of things there. Here, the elements are same as those are in first and second. They're the same thing as polynomials in high school or middle school, but we multiply with our ring multiplication. So we are taking R is any ring here. So these are not real numbers anymore. So we'll have to use the multiplication ring to do all computations. So as I mentioned, addition and multiplication is similar. And once again, R need not be commutative here. So interesting things are, if the original ring has 1, then the polynomial ring also has 1. But once again, I will go back to R commutative and polynomial ring is commutative, but I will be going back to my interesting elements. Oops. Here is one. So in general, of course, Rx need not be domain. That means product of two non-zero elements in a polynomial ring can be 0, which was not the case when you were in high school. So I've taken ring of integers, modulo 6, and gave you two examples here, f and g. If you multiply them under modulo 6, you'll see that is 0. Product will be 0. These, of course, are commutative rings here, so you don't have to be very careful here. But this one is a non-commutative ring, and here also I gave you two matrices, F and G. We're taking R is 2 by 2 matrix, ring over Z4, and your polynomial is 2x00. I wrote it in this form, but actually it is 2x00, and the other one is 2x 0, 2. Then now in this case, you see that product FG is 0, but GF is not 0 in it. So because now it's a non-commutative ring, you have to see both ways. So in the ring theory terms, these are referred to as left and right zero divisors. Those are beginning to run this stuff. So here is an interesting thing. So if R is a commutative ring and A is a polynomial, which is an idempotent, then A must be the constant term only. So in the case of commutative rings, idempotents in the ring come straight from the base ring. So you cannot have a polynomial, non-trivial polynomial, which will be an idempotent. Commutative ring is not necessary here. It's not that we have to have commutative ring. Even in non-commutative ring, with some additional condition, this also happens. For example, I can have only thing that I require that the term that phi of x must commute with every term, every other coefficient. So that means a sub 0, the term without the x, is commuting with every other coefficient, then also this result is true. Again, this was in one of the papers that I published in Journal of Algebra, this is one of the critical things in the paper for my results. This was just a lemma we proved, but I needed it to get lots of different results. In general, of course, there can be idempotent that are not in the base ring. So you can definitely have that. Here is an example. Again, I'm writing them as polynomials. I could have written this also as just 3x04, but since I'm talking about polynomial rings, I'm writing them as polynomials here. So actually this matrix is 3x04. And this is a non-trivial polynomial, which is an idempotent. You can check that. So this is an idempotent. Here is an interesting thing, that if A is any polynomial in a polynomial ring here, such that A squared minus A, now A is a polynomial, so A squared minus A is in the base ring. And the condition is that A sub 0, that the term without the x commutes with every other coefficient. And the last condition is 2 times A sub 0 minus 1 is invertible. Then that element must come from the base ring. So everything else will go away. So if you use all these conditions, of course, I can always show you the proof, but that's something those who are interested can easily prove. As a particular case of this, what we can do is, if A is an idempotent, then this condition E square minus E is in R is already there, and 2 times E minus 1 is a unit is also there, because those conditions are there. So that means idempotents will come from the base ring with that condition A sub 0 AI is equal to AI A sub 0. So that's the only condition that I told you earlier. So this is a generalization of the previous result that I mentioned. I'm writing them as questions. If R has no non-zero nilpotent element, then every unit in Rx, every invertible element in Rx is also in R. This is the condition is required, that R has to have no non-zero nilpotent elements. Then only it's true. In fact, the things are we studied the conditions like when every unit is coming from the base ring. Ashish has raised his hand. Okay. We'll take the question, Ashish, in a minute. In general, Rx can have units that are not in the base ring, even in the commutative case. Here's an example. We are taking the ring of integers modulo 4. And you can see that 1 plus 2x is, in fact, it's its own inverse. 1 plus 2x squared in this case is just 1. I'll give an exercise. These are simple things. Even if you're first year, second year students, you should be able to do that, assuming that you know how to multiply in Z4, ring of integers modulo 4. And that's where I told you that you multiply and take the remainder when you divide by 4. It's an interesting thing to get the basic understanding of these things. If every unit in a polynomial ring is in the base ring, then R have any non-zero nilpotent elements? The answer is no. So that means in that case, R will have only 0 nilpotent element. Again, that's an exercise I'm leaving for you. Some applications. Of course, in coding theory, ring theory is used in coding theory, cryptography. There are nice applications, and number theory. And who wants to be a millionaire here? Kaun banega crorepati? So this number, the problem is that is this factorable? And if yes, what are the factors of this? That's a nice number. These kind of problems take a lot of time, okay? Don't start doing this right away. How many possibilities are neither a sum of a cube and a prime nor a difference of a cube and a prime? They're interesting problems. Here's the final challenge of the day. I think I've already gone over. I'm hoping that I'm not keeping everyone. I gave you these two triangles. I want you to find x. And you can help me. Again, maybe you can answer. Do anybody have answers? First is 5, okay. Okay. I didn't say that. Somebody asked me, is the right triangle? I didn't say that. Yeah, I see that first is 5. Okay, I will repeat that. Less than 7. Okay. Less than 7 is a pretty broad answer. 4 less than x less than 7. Lots of answers there. Yeah, I hear that first is 5. I think I should move this guy here so that people can see my screen. Okay, I think I should share my answer. Good answers though. So here's my answer. Do you see my answer? Notice that I didn't say find the value of x. I just said find x. So you're saying me is 5 or things like that. I didn't tell you to give me the value of x. I said find x, and x is right there. Yeah, just for fun. So what's the tip for today? We have to have, this is what I got from Deshbandhu College. I need to have strong foundation and good foundation. And that's what Deshbandhu College gave me. Stay focused. See, we live in the 21st century, and there's so many 21st century distractions. Whether it's Facebook, Snapchat, this chat, that chat, Instagram, everybody. But when you're doing mathematics, keep everything away from you. Read the problem carefully, like I just gave you the problem. I want read carefully, understand, analyze, and then solve it. When I said find x, I didn't say find the value of x. I tell you one thing. Somebody asked this question. I'll show you that in a minute. And importance of why. Why I'm doing it. What's the use? If you do all these things, that'd be nice. So let me tell you one thing quickly here. This is the question somebody asked on an exam, not me. So the question was expand x plus y to the power 3. And student wrote that answer. X plus y.
Sorry, sir, your screen is again not visible.
Okay.
Please share it again.
Why does it do that? I'll
I don't
stop
know.
and then.
It's just showing the idempotent matrix. That's it. We
Okay.
can see all of that.
Oh, okay.
Change the page.
I know what happened. I know what happened. I will just share down. Oops. Not that one. This one. Now you can see it.
Yes, we can see it now.
Yeah, now it is coming.
Yes, sorry, because I changed the slide there, so it was showing the old one. So it's
Yeah, that. Okay.
expand this one, and student wrote this answer. He wrote this equal to x plus y equal to x plus y. So he is expanding also because he didn't know how to do it. But he said, I expanded. The question is expand. So he expanded it. So this is what I'm saying. We have to read the question carefully, understand it. And as teachers, we have to phrase the questions carefully so that students understand what we mean. So that's what my problem that I had on the screen. When I said find x, I should have said find the value of x. So that's where we have to be careful as teachers, and students have to analyze and carefully read the question. And other thing is accept the challenge and never give up. And mathematics, when you do this, I'm talking to first year, second, third year students, you'll have lots of challenges. Teacher will give you, professors will give you problems. There'll be challenges, but never give up. Whether you are driving, riding in a bus or anywhere, this is what I used to do when I was doing my MPhil at Delhi University. That was Dr. Agarwal was talking about earlier also. So sometimes we were coming home from college, we will be discussing those things in the bus. So these are some things, and I think it's almost time, and I would thank everyone.
Thank you, sir. Thank you so much for your informative and interactive, interesting, and student-friendly approach for the presentation. I hope all have enjoyed so much. And of course, my thanks are to you for your very good feedback for the college and inspiring our students with your piece of advice. Now I ask Dr. Pankaj Mishra and Dr. Preeti Gupta for interactions. They can take the questions of the audience with Dr. Pramod Kaur.
Hello, I'm audible?
Yes, Pankaj, you are
Hello.
audible.
Okay,
Yes,
okay.
I can hear
Thank
you.
you, sir, for
Yes,
such
you
a
are audible.
thank you, sir, such a wonderful lecture. Sir, actually, I did not receive a question from YouTube and as well as Zoom, so I request the directly to the Pramod sir. If they can raise hand, actually. I request the participant, they can directly ask the question to Pramod sir.
Okay. Attendees, please ask your questions by raising your hands. You can directly interact with Professor Pramod Kamar.
So I
Just
see Dr. Shweta has hand up.
yes, yes.
Dr. Shweta.
Shweta,
Dr.
Monica
Shweta,
Arora,
you are
Vish-
muted. If you have a question. Okay. Okay, I'll go to Dr. Harish Chandar. I see your hand up. Can you hear me?
Mr. Harish.
Hello. Hello. Hello.
Yes, Dr. Harish.
Hello. Hello.
Yeah,
No,
I
sir,
can
can
hear
you
you.
hear me? Can
Yes,
you
I
hear
can
me,
hear
sir?
you. Yes.
Yes.
Okay. Yes, sir, I am Harish from JNK.
Uh-huh.
Sir, it was a nice session. It was an informative one, sir. So I am feeling honored, sir, to be a part of this conversation, sir.
Thank you very much.
ओके सर, तो आपने जो इडोम्पेटेंट मैट्रिसेस के बारे में बताया सर, तो मैं ये चाहता हूँ कि सर इस पे एक सेशन अगर जिन्होंने भी ये वेबिनार ऑर्गेनाइज कराया है, तो इस पे एक डिटेल सेशन सर अगर हो जाए इस पे इडोम्पेटेंट और नीलपेटेंट मैट्रिसेस पे सर, तो इट वुड बी ए नाइस.
Sure, sir. We'll try to arrange it as early as possible.
Sure.
We can.
Okay, ma'am. Thank you very much. Thank you very much, ma'am. Usha, ma'am. It was a nice session. It was an informative one.
Yeah, it was really very nice. Hope everyone is equipped with the knowledge of this, and the student-friendly approach was really amazing. What I say.
Yeah, absolutely, ma'am, absolutely. And most probably it was my first session. It was my first session.
Okay.
Okay, and I am feeling honored, ma'am. Thank you very much.
Okay, thanks, Harish.
Okay, sir. Okay.
So next, I'm going to Dr. Shweta. Dr. Shweta.
Hello.
Dr. Shweta, can you please
Good
write your
morning, sir.
question in the
Hi.
chat window?
Yes. Good morning, sir. Sir, can you hear me? Yeah,
Yes, I
yeah,
can
we
hear
are.
you.
Yes, yes, you are audible.
Yeah, sir, I actually wanted to ask that you have taken up clean elements. Sir, why do we call an element as a clean element? And sir, what properties of ring can we get if we study the clean rings? Like if every element can be written as the sum of the clean element and then unit. So, sir, why do we study these rings? Like, what does it? What is the usage of this?
The study actually started in the mid 70s, in 77, 78, and it gained a lot of momentum in the 90s. But right now, they are not many people because the study came essentially from C-star algebras and operator theory. So that's where the use was, and that's where people were using, and that essentially they were not studying. Now, when you see the element clean, you should not get an impression that there are dirty elements also. I do not know why did they coin the word clean. I have no idea. Nicholson coined that term. Probably they could not find another term at that time, so they just called them clean. And there are lots of properties on that. There, one thing is definite. In fact, when I did my work on idempotence, actually my goal was on clean elements, but for that I was started looking at idempotence. So answering your question, why I do not know why did they call clean. Probably they could not coin another word at that time, and they just picked up the word clean. And after that, there are lots of different words have come: strongly clean and weakly clean, and lots of different things are there.
Hmm.
Most of these things were done in the 90s and early 2000s. And like even there are properties, module theoretic properties like injectivity and continuity, the continuous rings, etc. This whole thing was studied in the late 90s, early 2000s, and they proved that the continuous rings are also clean. So those are the things that happened, and a lot of work is done at that time. These days, not much is being done, but there is still a lot that can be done.
Okay, sir. So what I feel is that you can divide the ring into two mutually exclusive sets. Like since you are writing as a sum of them, so will
Yeah,
it be the direct like representation, as in sum of the
not
two, and those
not
sets would be mutually exclusive sets?
not necessarily. So that's and these two sets, the units will do form a group, but the idempotents don't even form a ring or group. So those individual sets may not have much properties.
Okay. Hmm.
Any other
Okay, sir.
questions? Sir? Okay.
Yes, sir. Thank you, sir. Thank you.
Next, let's go to Monica. Monica.
Sir, good morning.
Yes, Monica. Yeah.
Bill?
Yes, yes, you can ask.
Right. So my
I can hear you, Monica.
why is a ring called a ring? Do we have some geometry associated with it for the purpose of calling a ring to be a ring?
No, I didn't. As I mentioned that Hilbert came with that idea. Initially, this word was not ring. Hilbert gave that idea. He was studying something, so I am not completely sure why he called it ring. I started calling ring because I was taught that it's a ring. So I didn't look into that, and I can definitely look into why. But I don't think I can find anything. But Hilbert gave that idea, and then since then, the word ring is popular. If I find something else, I'll send
All
something
right.
to someone.
All right. All right, sir. All right. Thank you so much. Thank you.
Ritu Arora. Ritu,
Good
good afternoon. You are muted, Ritu.
I'm trying to, yeah.
Okay, you're
One
okay.
of my question has been answered. I had asked why a ring is called a ring. Is there any geometry behind it? In fact, I was asked this question in an interview. by
Okay.
Professor Ajit Iqbal Singh, if you remember. She's our teacher. So I didn't have answer, and it has been many years, and I have not got the answer even today. So that's why I asked.
Okay.
Uh,
Fine.
Another question that I have is, like, we have, since you're from algebraic coding theory, we have codes over vector spaces, like fields. Vector spaces are over fields. Do we have any structure over rings also? Any such structure over rings, which we are actually using in our research? Or my research field is actually algebraic coding theory only. So I was just wondering if we have something over rings also, which we are practically using.
Yes, in fact, I don't have much work in coding theory now, and my first article was in coding theory, and that was the course over ring of integers modulo 4, modulo n. So you did not need a field there, and my paper is the ring of integers, the course over cyclic course over ring of integers modulo 4. So there are lot of work done now with rings. So my work was only on integers modulo n, but now there are several different rings, even perfect rings, etc. There are lots of things that happen. All those Maxwellian conditions, etc. Maxwellian conditions, they're all available now. In fact, there are conditions that connect perfectness of a ring with Maxwellian conditions. So yes, there are a lot of literature available, and a lot of people are working on codes over rings.
Okay. Thank you
My
very much.
paper, of course, is in 1998 in finite fields and application. I think it's 1998, somewhere around that. So that was my first article. Even
So do they have more practical utility over the vector space over fields, or I mean, they're at par, or there are some drawbacks?
The several things go smoothly, as there are sometimes you have to have additional conditions. And of course, there are codes that people did not understand those codes, the geometrical codes I'm talking about. People did not understand those codes until this association with the rings, because those were the geometric codes. They were actually have structure over rings, and they are available, those codes. I can send you the reference to somebody. Yes,
Yes, sir.
there are several codes. So if you look at my paper also, cyclic codes and quadratic residue codes over integer modulo n, and you will find that. And also before me, what I did was, before me, Vera Plus, she did the work on integers, codes over integers modulo 4.
Okay.
And I generalized to anything, and that is an article that
Thank you. Thank you very much, sir. And the session was really very, very informative, very interactive. Thanks for the wonderful session.
no, thank you very much. Dr. Vinod Kumar. Dr. Vinod Kumar, are there? Dr. Vinod Kumar.
Hello. Hello.
Yes.
Audible, you're audible?
Okay.
Yeah, I can hear you.
Okay, so good morning, sir.
Good morning.
Sir, actually, I'm working in cryptography and information security. So, sir, any application of ring in use in cryptography? You have any idea? You please share me.
But I don't have any work, but I have heard a lot of people are using ring theory. Even an ID Delhi, Dr. R.K. Sharma, he is doing a lot of work, and he uses ring theory in cryptography. So there are a lot of people are using. This is becoming kind of a back. But as far as I'm concerned, I have not done anything, and I don't have any first-hand knowledge that I can give you at this point. But I can always find people who are working on this. And a lot of people are doing coding theory and cryptography, and then using rings in this.
Okay, sir. Thank you so much, sir.
Okay, thank you. Dr. Nitin. Dr. Nitin? Nitin Kumar?
Yes, sir. Yes, sir.
Uh-huh.
Good morning, sir.
Good morning.
Sir, sir, my question is, sir, in the coming time, we can tell some areas for generation that can be worked out, especially in the mathematics.
I didn't get your question. Can you repeat your question, please? Nitin, can you repeat your question, please?
Hello, Nitin. Hello. I think, sir, he's disconnected.
Okay. I still see him, but okay. I think I don't have any other.
Ashutosh Rajput. Hello.
Okay, I think
Sir,
participant has
Mr. Ashutosh Rajput wants to ask a question.
Yes, sir.
Is there any standard method to determine the sign of eigenvalues of a high ordered matrices?
Ma'am, I also want to ask a question, sir.
हाँ सर पूछिए हाँ you are welcome. You ask the question, you repeat your question.
In the coming time, we can tell some areas for generation that can be worked out, especially in the mathematics.
Oh, there are lots of areas. It depends on the interest of the person. What area you're doing, like whether you are going to algebra, analysis, operator theory. There's so many. It depends on every single field. Now, in algebra, also you have group theory, ring theory. So my main work is ring theory. So in the area of ring theory, there are several. I already told you, Leavitt path algebra is the burning hot topic, but that's just one topic. A lot of people are working on idempotence. A lot of work is, sometimes writing idempotence as a product of some other idempotence, or writing idempotence some of other idempotence. People just pick up one problem and do this. So lots of things are going on in all these fields. Finding the injectivity-like conditions. Like there's so many generalizations of injectivity, like CS rings, etc. The other day, just last week, Friday, somebody was giving a presentation on Bayer rings. Lots of things are happening. We have to narrow it down to what somebody is interested in, and then we go from there. So, of course, I'm not expert in everything anyways also. So, as I said, I have done some work in idempotence, some work in this Leavitt path algebras. And my original work as a PhD student was on injectivity-like conditions. So from there, it went to clean because there was a connection. I started to do some work in clean rings, and then idempotence. I came as a byproduct, but I started liking that. Also, all these were connected. It's not that I was just going. Somebody proved that my work was on continuous rings, and the continuous rings, somebody proved that continuous rings are clean. In fact, the proof was continuous modules are clean. So I had to see the connection with clean, and then clean elements required idempotence. So all these things are there. Leavitt path algebras, that's one thing. A lot of people are doing work. And then you have queer algebras and several different things. Okay. So there are lots of things, but it depends on what area you want to work in, algebra or applied mathematics or analysis or anything. It depends on that. Does that answer your question, Ridin? I think we can move on to the next one.
Yeah. We can to move next one. Harni ma'am, kindly proceed again.
Okay, sir, a virtual round of applause for you for your presentations and your interactions with the participants. Now I ask Dr. Harindra Chaudhary for a formal vote of thanks.
Thank you, Usha ma'am. Good morning to all. I feel privileged to get a chance to present the vote of thanks on the behalf of Department of Mathematics, Deshbandhu College. Firstly, I would like to express my sincere thanks to Professor Pramod Kanwar for delivering such an excellent talk on a journey from integers to the rings. It was a very well organized talk, starting from integers to connecting to the graph theoretical concepts. It was indeed a pleasure to listen to you, sir. And everyone will agree with me that after attending this wonderful session by you, we are all become a very big fan of you. You are an ultimate inspiration to all of us. I once again thank you, sir, for sharing your such a deep knowledge with all of us. Thank you, sir. Now I would like to thank our very young, talented, dynamic principal, Dr. Ajiv Agrawal, for his unconditional support to the Department of Mathematics for organizing such an event. Also, my special thanks to our very young, energetic, enthusiastic teacher in charge of Mathematics Department, Mr. Chandrasekhar Azad, for helping me out in every possible way in organizing the event. I also extend my thanks to our very loving and caring senior colleagues, Dr. Usha Rao ma'am, Dr. Pramod Kumar Arora, Dr. Naveen Chandra. I have been fortunate enough to be backed by a team of very young, motivated and highly dedicated colleagues of maths departments who work day and night to organize this event. For instance, I would like to thank Mr. Rohit, Mr. Mukesh, Ms. Saloni, Sushil, Sunil, CP, Chirag, Parveen, Bikender, Pankaj, Bhagwat, Dinesh, Shipra, OP, Manoj, Rajendra, Preeti, Y. Preeti ji. I also thank Dr. Aditya Saxena, Coordinator IQAC, and Dr. Monica from Computer Science Department for their timely help and support provided for organizing the event. I would be failing in my duty if I don't thank the participants from various colleges and institutes all over the India attending the talk. Last but not the least, I would like to thank all the participants, including teachers, students, colleagues, for attending this webinar, making this webinar a great success. In the coming time, as I mentioned earlier also, that in the near future, we will organize many more such webinars of this type. And maybe we'll invite Professor Dr. Pramod Kanwar again for explaining in detail the idempotent matrix element and the nilpotent elements. As one of our participants demanded that there should be a lecture on these two topics. So, sir, be ready with one more lecture on ring theory, and more topics will be organized on. Will be organized many more seminars on various topics. So, thanks once again, everyone, to attend this webinar. Thank you, sir. And till then, I wish you all the good health for all of you. Stay home, stay safe, stay online. Jai Hind, Jai Bharat, Shresh Bharat, Ek Bharat. Thank you. Dhanyavad.
Thank you, Dr. Harindri, for such a nice vote of thanks. But before we wrap up, let's stand for national anthem. That's the tradition we are taking. So please stand up for that. Wait a minute, please.
शुभ आशीष मांगे गाहे तव जय गाथा जय गण मंगल दायक जय हे भारत भाग्य
Thanks again. So, as it is said, good events never end, they just take the pause. So looking forward for such many more events under the leadership of our very young teacher in charge, Dr. Chandrasekhar, we say we can now conclude the session. Thank you, everyone.
Thank you.